In this presentation, I will talk about the computer simulation work we carried out to understand how thousands of kilometers deep vortices and jet streams may form in the atmospheres of Saturn and Jupiter. This work was carried out in collaboration with Professor Jeremy Bloxham and Professor Moritz Heipel. Let's first familiarize ourselves with few amazing observations that have been gathered through the past decades about these planets. When you look at Saturn, it kind of looks like a yellowish grayish ball. I'm showing you the Earth as a comparison to give you a sense of how awesomely large the planet is. Observations gathered over the last decades have provided us with a rich and detailed view of the atmosphere of Saturn. When you look closely at the surface, you will see a thin layer of clouds and haze shrouding the entire planet. This layer of cloud is on top of some large-scale atmospheric features which can be better revealed by some image enhancements. Broadly speaking, we have two major features on Saturn's surface. It has localized storms, which are essentially giant fluid vortices. And it also has these magnificent east-west jet streams that go around the planet and persist for decades on end. And some of these jet streams have been present since we started observing Saturn. Saturn also has another magnificent feature called the polar hexagon, which is essentially a jet stream shaped in the form of a hexagon. It was first discovered in 1988 when scientist David Godfrey put together a bunch of pictures taken by Voyager 2 around 1981. This hexagon stayed undetected for almost a decade because unless you project the images to a proper orthographic projection, it is hard to make out its shape. In later years, Cassini spacecraft provided spectacular views of the northern polar hexagon. Wait, there is more. If you look directly at the rotation pole of the planet, there is a large storm which has pretty much remained unperturbed for as long as we have seen it. Unlike the hexagon, which exists only in the northern side of the planet, both poles of the planet have such a large circular storm at the rotation pole. Okay, that is enough for Saturn. Now let's look at what kind of interesting features Jupiter has. Fortunately, unlike Saturn, Jupiter's atmosphere has a lot less haze. That allows us to really appreciate all the details present in the atmosphere without much image enhancement or anything like that. In this slide, I'm showing you a time lapse of images taken over a time period of 32 Earth days by Voyager 1 around 1979. I remember seeing this animation when I was in my undergrad, and I was utterly amazed by the richness of the fluid dynamics present here. In the animation, you can clearly make out different storms as well as different jet streams that are present on this planet. In the last 5 years or so, thanks to the NASA's Juno spacecraft, the level of details we have been able to see on Jupiter's surface is nothing less than spectacular. The image here shows storms and jet streams and everything in between that engulfs the surface of the entire planet. Similar to the poles of Saturn, Jupiter's polar atmosphere is also quite interesting. Now, it doesn't have any fancy hexagonal jet streams. However, it has a rather well-defined cluster of storms, where one storm lies right at the pole and a bunch of others surround it in a regular fashion. This regular arrangement of storms becomes clearer if we do some image enhancement. It shows one polar storm and 8 surrounding storms. And similar thing happens on the south side of the planet. Some of you might already be eyeing this giant red feature sitting in the image. Well, you are not alone in being intrigued by this large feature. Back in 1665, which was 365 years ago, an astronomer in the Paris Observatory, Giovanni Cassini, noticed this feature on Jupiter and recorded it using hand drawings in his journals. This tells us that at least this dark feature called the Great Red Spot has been present on the surface of Jupiter since 1665. That's quite amazing. Of course, the NASA Juno spacecraft has provided a much more detailed view of this red storm. We can see that it's not just a standalone swirling vortex, but has intricate features within itself. Now, just to give you some numbers, the wind speeds of the jet streams that go around the planet are shown for both planets on the plot. The wind speeds can reach 1,000 kilometers per hour. They also alternate in direction, where some go from west to east while others go from east to west. Well, these winds are absolutely insane and are nothing like anything we see on Earth. Such insane winds actually do have some real life benefits. At least in my case, when I imagine about these winds on these large planets, I usually get much calmer about the 100 kilometers per hour winds we get here in Boston. So it makes life a bit easier, at least in my imagination. So hopefully by now you are also amazed by the incredibly rich dynamics present on the surface of Saturn and Jupiter. As a scientist, one of the first questions that will come to mind is what drives them? And when you realize that these planets don't have any solid ground, another question is how deep are these atmospheric features? The second question is particularly interesting because its answer relies on how the jet streams are driven. Scientists have been trying to answer these questions related to jet streams and vortices for decades now. Broadly speaking, two schools of thought have emerged over time. One assumes that these features are similar to the atmospheric features on Earth, likely paper thin in nature, which implies that much of the dynamics in the north-south, east-west direction, and there's not much happening in the radial direction. So in this interpretation, the depth of the storms and jet streams on Saturn and Jupiter is perhaps in the range of tens of kilometers, which is very thin in the context of these large planets. Many of the modeling ideas that have been used in the Earth atmospheric physics have therefore been exported to these planets. For example, the shallow water hydrodynamic equations are commonly used in this community. And one of the primary mechanisms for driving these features on Saturn and Jupiter is expected to be moist convection physics. The other community of scientists expect that the jet streams and some of the storms on these large planets could be thousands of kilometers deep. In this interpretation, the atmospheric features are nothing but surface manifestations of the fluid dynamics happening deeper into the planet. In the deeper part of the planet, the motions are likely driven by the planetary convection that is helping the planets cool down over time. I subscribe to this school of thought and will discuss in detail some of the progress made in this community. But I must emphasize that this does not mean I exclusively support this approach. This is very much an active area of research, and progress is made on both fronts routinely, and the final word is yet to be said on this issue. Who knows, in the end, both approaches might be needed to explain the extremely rich atmospheric dynamics of these giant planets. Before we proceed further, it's worthwhile to get some idea about how deep can storms and jet streams penetrate into these planets. Jupiter as well as Saturn can largely be approximated by a handful of layers. The innermost layer is likely a rocky core made of silicates. On top of it, there is a large volume that contains something called metallic hydrogen. On top of it, there is a region where liquid hydrogen without metallic properties resides. Then comes the gaseous hydrogen layer, which itself is surrounded by the outermost cloud layer. It is this cloud layer which we see through observations. At this moment, you may be wondering, what the hell is this metallic hydrogen thing? It has been predicted that as the temperature and pressure increases deeper into the planet, hydrogen may undergo a phase transition and turn into something called metallic hydrogen. As the At the increased pressure and temperature situations, electrons may be able to completely separate from the nucleus and take up a more metallic nature as compared to just simple hydrogen. When that happens, the electrical conductivity of hydrogen can increase by orders of magnitude. With increased electrical conductivity, the metallic hydrogen can actually act as a fluid dynamo, driven by the motions of the planetary convection. This ends up producing rather strong magnetic fields which do not like very fast flows. Therefore, there is effectively an upper bound on the depth of the atmospheric features above which magnetic fields will strongly truncate them. For Jupiter, this upper bound is about 1,000 kilometers, while for Saturn, it is a couple of times larger than that. Since we have hypothesized that convection is likely the key ingredient in driving the jet streams and vortices on Jupiter and Saturn, let me say a few words on a very important property of convection. You might be familiar with simple natural convection, where fluid motions transport energy from hot parts to cold parts. The process happens in a rather chaotic way. As shown by the plot on the left-hand side, the isosurfaces of temperature in a typical convecting system are all over the place. However, when the convective system rotates, something rather interesting happens. Instead of looking like chaotic flow patterns, convection takes the form of columns that are aligned with the rotation axis of the system. They're commonly called Taylor columns and are produced by the two-dimensionalization property of Coriolis forces in a rotating system. If someone is interested in more details, check out the famous Prodman-Taylor theorem on this topic. But for the time being, it's enough to know that convection forms these columns. This is actually how these fluid Taylor columns look like in an actual laboratory experiments. They are not nicely laminar structures, but they do have some turbulence associated with them. But largely, they are all aligned with the rotation axis. Taylor columns have very interesting properties when they occur in cylindrical or spherical systems. Back in 1976, Friedrich Busse analytically showed that if such fluid Taylor columns are present in a rotating cylindrical container with curved boundaries on top and bottom, they can redistribute the angular momentum in such a way that some parts of the fluid rotates faster than the container rotation, while the other parts of the fluid rotate slower. This behavior ends up creating very fluid flow that looks really like the jet streams we have discussed so far, where some parts of the fluid are rotating faster than the container and the other parts are rotating slower. If you can now picture a spherical shell to be composed of several cylindrical containers having Taylor columns, then we can imagine a scenario where most of the jets visible on Saturn and Jupiter are surface manifestations of these deep jet streams driven by the fluid Taylor columns in rotating convection. When this idea was proposed in 1976, there wasn't a way to actually model such a system in high enough complexity to test it. That changed in later years when computers became much more powerful. In the 21st century, with modern computers, researchers started modeling the thermal convection happening in a spherical shell with 3D nonlinear fluid dynamics. By changing the thickness of the spherical shell, they could incorporate different regions of a planet into the model. So spherical shells are really important in this community. In 2001, two groups came out with results that showed the formation of multiple deep jet streams that were driven by rotating thermal convection. This was an exciting result because it showed that only rotating thermal convection can generate jet streams. On the leftmost plot, we have the convection plumes in the system, which drive the middle panel jet streams shown here. And if you look at the surface, they do have some similarity with the profile of jet streams we see on other planets, Jupiter and Saturn. A few years later, more sophisticated models came out that produced more realistic looking jet streams. This model showed numerous alternating jet streams, along with signature strong eastward jet stream near the equator of the model. This model demonstrates that rotating convection is a promising approach for modeling jet streams when it comes to planets like Jupiter and Saturn. Fortunately, we are living in a time when we can actually observationally infer the depth of the jet streams on these planets. In 2018, the observation results from Juno satellite came out, and they showed that jet streams on Jupiter are thousands of kilometers deep. About a year later, the data from the Cassini spacecraft came out, which showed that the jet streams on Saturn are even deeper, possibly extending to 9,000 kilometers. So at this stage, we can say that jet streams are likely very deep structures. Now, one can ask, what about the vertical storms in the system on the surface of Jupiter and Saturn? Can they also be thousands of kilometers deep? Deep vortices, that are essentially storms, are actually well known in rotating convection in Cartesian box simulations. Here is an example that shows one vortex that is generated in a box simulation and is aligned with the rotation axis that's coming out of the plane in the left-hand side. As we discussed earlier, fluid flows in rotating systems like to have less variation along the rotation axis and tend to align with it. We can see this behavior in the right-hand plot, which shows a cut through the box along the rotation axis. As I showed earlier, modeling jet streams has been possible in rotating spherical convection simulations. However, finding such coherent, large-scale, multi-scale flow vortices has been quite challenging in the spherical shell community. This brings us to our work. I must admit that unlike several earlier studies, we were actually not trying to model some particular phenomena occurring on Saturn and Jupiter, be it a jet stream or a storm. We simply asked, what's possible if we assume that the outer layers of these planets are undergoing rotating thermal convection? Under this assumption, we changed the primary control parameters of the fluid dynamics and investigated what kind of features formed spontaneously. We changed the thickness of the shell to probe different depths of the atmospheric layers. In some of the cases, we also included a deep dynamo layer to model the interaction of an atmospheric and a dynamo layer. I'll come back to it later. We used an open source code called MAGIC, which solves the magnetohydrodynamics of fluids in a spherical shell. It is a fully spectral code in the spatial direction, where it uses spherical harmonics in the latitude and longitude direction and Chebyshev polynomials in the radial direction. The code shows very good scaling, and it can go up to 10,000 CPUs. Now, these are the generic equations solved by the MAGIC software. I will not go too much into the details, but we say that the fluid motions are governed by the Navier-Stokes equation and the incompressibility of the momentum. The magnetic fields, the magnetic field behavior is governed by the magnetic induction equation, while the energy conservation gives us the evolution equation for the thermal variable, which is in this case considered to be the entropy rather than the temperature. If someone wants to get more, basically get more details about the model, they can certainly check out the manual whose link I've given here. And we can, of course, talk about it after the talk. For our investigation, Rayleigh number and Ekman number were the main control parameters. The classical Rayleigh number essentially determines the convective vigor, allowing us to adjust the level of turbulence in the system, while the Ekman number is a rough measure of the influence of rotation force on the flow. We changed these parameters, along with the spherical shell thickness, to scan different turbulent regimes that may be applicable to Jupiter and Saturn. Although we carried out a large ensemble study, I will present here only 3 cases that showed incredibly rich dynamics that happens to be quite similar to Saturn and Jupiter. Let's check out the first case, where the shell thickness is about 10% of the spherical radius. This is somewhat similar to the hypothesized depth of the jet streams on Saturn. Let's see what kind of flow features arise when we model turbulent thermal convection in such a shell. Here is the emergent zonal flow, or more generally called jet streams, in the model. On the left-hand side, I'm showing you the zonal flow on the surface of the simulation, which can be directly compared with the surface jet streams observed on Saturn. To be completely honest, we were kind of surprised by a rather good match with the actual zonal flows observed on the surface of Saturn. Not only were they qualitatively similar, but also quantitatively similar within a factor of 2. On the right-hand side figure, you can see the depth profile of the zonal flows. They don't change much as a function of depth, and depth here is defined in the direction that's parallel to the rotation axis of the system. So very much like how Friedrich Busse imagined in 1976, the jet streams are actually depth-spanning cylindrical features aligned with the rotation axis. This has been known, the behavior of jet streams in this kind of shells is known for quite some time. When you look at the actual flow profile, it reveals even more interesting dynamics. The mid to high latitude zonal jets are not just circularized jet streams, but have distinct shapes in the form of polygons. In particular, if you look at the 60-degree north jet, the polygon shape is immediately apparent. And we can easily make out the number of edges present in this jet, which happens to be 9 here. If you look a little closer, you can see that the edges and the vertices of the polygons are accompanied by large vortices. So what we believe is happening is that zonal jets and large vortices need to coexist in mid to high latitude regions. In order to settle together, these storms end up pinching a zonal jet, giving it a polygonal shape. It is hard not to compare it with the hexagonal jet in Saturn. We can imagine that there too storms are helping to shape the hexagonal jet. The model doesn't exactly produce six sides, but the fact that it produces a polygonal jet is exciting enough. Furthermore, the simulation also has a storm right at the pole, similar to Saturn. Now, some of you might already be wondering, why is that Saturn shows only hexagonal jet and not the associated giant storms like we see in this model? We think we might know why. Let's investigate the flow profile as we come closer and closer to the outer boundary of the simulation, which would be equivalent to the visible surface of Saturn. The plot here shows the flow profile at a surface that is 5% below the outermost radius. This profile is at a surface that is 3% below the outermost radius. This is at 1% below the outermost radius. And this is at just 0.7% below the outermost radius. I hope you have realized that as we come closer to the surface of the simulation, polygonal jets keep their identity while the storms that are pinching them get washed out. Let me go through the images again. At 5% below the surface, 3% below the surface, 1% below the surface, 0.7% below the surface. We think the main reason is that the more chaotic and incoherent flows near the outermost boundary of the simulation, they smear out the slower flow in the storms. However, the stronger flows in the jet stream survive all the way to the top. The stronger flows in the outer layers are quintessential features of compressible convection, where deeper flows tend to be a bit more laminar, and the shallower uh, parts of the fluid that are all lighter in nature, they tend to be more turbulent and chaotic. A similar scenario can certainly be possible for Saturn, where compressible convection is undergoing all the time. This is just to dazzle you now with a pretty movie of the flow in the simulation so that you can really appreciate the rich fluid dynamics here. Jet streams and storms are clearly visible and interact with each other in highly nonlinear ways. And the movie is, I have to admit, is really psychedelic. It's really a pleasure to look at it. I'll stop here a few more seconds and then we can move on. Okay, now let's go to the second simulation. Here the shell thickness is thinner and is about 3% of the spherical radius. Let's see what kind of flow features arise when we model turbulent thermal convection in this shell, which is substantially thinner than the earlier one. Once again, I'm showing you the zonal flow profile on the surface on the left-hand side. Here, what is noteworthy is the presence of very strong westward jets at about 18 degrees south and north. If you look at the depth profile of these jet streams on the right-hand side, they again behave as cylinders aligned with rotation axis. In this thin shell simulation, the emergent behavior is substantially different from the earlier case. Unlike the earlier case, where we had rather large storms, here we get a lot more, but smaller ones. If you pay attention to the mid-latitude region, you will see several patches of vorticity in red color, which means they are cyclonic in nature. If you look at the high latitude regions, there are more blue clumps of vorticity, implying anticyclones. This behavior is due to the background direction of the vorticity set by the local shear flows in the jet streams. In the mid-latitudes, the jet stream shear is cyclonic in nature, which is essentially anti-clockwise in nature. And that helps to produce cyclonic features. While if you go to the high latitude regions, the direction of the shear is reversed, and that helps to produce more anticyclones in nature. These and something similar has been observed on Jupiter as well, that the local direction of the jet streams uh, sort of dictates the nature of the storms embedded into them. Now, I'm showing you this movie just to show you, just through purely visual inspection, the incredibly rich dynamic behavior in the simulation is quite reminiscent of what's happening on Jupiter's surface. Now, we're not comparing storm to storm, jet stream to jet stream, but just by looking at it, you can see that they are at least qualitatively similar. Now let's look at the details of the flow without an east-west component to highlight local vertical storms. Since there is a lot of information here, let's zoom into some regions. First, in the polar region, shown by the white box. You can clearly see numerous vortices that are scattered all over the place. And if you recall the situation in the Jupiter's polar atmosphere, then there is certainly some similarity. Again, the similarity is qualitative here. We're not trying to match storm by storm, but it basically looks quite similar. Now let's zoom into a region that's closer to the equator rather than the pole. Here, the number of storms are fewer, and the occurrence of large storms is more prevalent than smaller ones. This is also somewhat similar to Jupiter, where storms become less prevalent closer to the equator. Now let me show you the exact flow structure inside two of the storms. First is shown here by the white box. This one is a cyclone rotating in an anti-clockwise direction. The storm exists in the entire depth of the simulated spherical shell. Let's look at another one at a different location. This one is an anticyclone rotating in the clockwise direction. Now, just to summarize here, this simulation shows a very rich hydrodynamics. It produces numerous storms and jet streams and captures their complex interactions. Of course, the results are only qualitatively similar, as I mentioned earlier as well. Surely more work needs to be done, but regardless, it is very promising first step, and something like this hasn't been seen in earlier simulations. Now let me show you some results from the third and the last case, where we model a much deeper spherical shell to investigate how magnetic fields may affect the dynamics in the outer layers of Jupiter or Saturn. This simulation domain covers 90% of the radius of the spherical shell. To self-consistently model magnetic fields, much like what happens in the actual planets, we also increase the electrical conductivity of the fluid we model as a function of the radius. This self-consistently sets up a dynamo layer which produces a dynamo, while the outer layer where the low conductivity, which has low conductivity and mimics the atmospheric layers of Jupiter and Saturn, the presence of that layer on top of the dynamo layer allows the possibility of some interaction. And that was the whole point of modeling this simulation. Now, in this case, the zonal flow profile is substantially different from the last two cases. There are no jets in mid to high latitude regions. This is mainly due to the suppression of zonal jets by the inner dynamo layer in low to high latitude regions. The hydrodynamic layer, which is present in the outer 15% or so of the radius, allows the existence of a single eastward oriented jet. So in terms of zonal flow, it's not very interesting. However, it's completely different if you look at the other flow component. The details of the other flow components were really interesting and highly unexpected in this model. My apologies for the rather dense plot, but hopefully as I'm going through it, it'll make sense. As I already mentioned, there is hardly any jet streams except for one near the equator, which is visible by this pretty bright yellow region in the top two plots. However, when you look at the flow profile on the outer surface of the simulation, very interesting features are clearly visible, uh, which are basically yellow patches at mid to high latitudes. In mid to high latitude region, although the simulation does not produce much zonal flow, it produces localized concentrations of large vorticity. When you look at the flow profile of these local vertical features shown on the panel C, all of them are anticyclonic in nature, and most of them have a quiet core with the outer edges carrying most of the vorticity. And when you look closer at the deeper flow profile associated with these vertical flow structures, we find that there is a shaft, fluid shaft, essentially connecting these features with the inner dynamo layer, which is below this gray region in this plot. It turns out that these features are formed when a convective plume comes from the dynamo layer every once in a while and manages to survive the convective turbulence in the overlying hydrodynamic layer. This plume then hits the outermost layer because there is nowhere else to go after that. When that happens, the plume diverges and the background Coriolis force turns it into an anticyclone. So interestingly, it appears that deep dynamo layer is capable of exciting features on the surface of a hydrodynamic layer, which is entirely unexpected, and it was quite surprising. So we are hypothesizing, driven by the results from this case, that Jupiter's great red spot might be a storm that was triggered by a large convection plume coming from much deeper layers. It is a rather radical uh, hypothesis compared to what people have imagined in the past about how such a large storm can form in Jupiter. Now here I'm showing you the radial velocity near the surface of the simulation to show you how these large storms evolve. You can clearly make out all the local disturbances that are driven by convective plumes hitting the outer layer. Some of those convective plumes that live long enough show a slow westward drift in the low latitude region. You can check this out here. Interestingly, Jupiter's large red spot also shows a slow westward drift. Uh, Connecting the origin of the great red spot with the deeper dynamo layer might be one way of circumventing the issue of generating a great red spot through purely hydrodynamic turbulence, which seems to be a rather challenging issue and is not so straightforward. But in this explanation, it spontaneously arises through through dynamo through the dynamo layer, which every once in a while throws out these giant plumes. All right, now we can wrap up. Uh, I'll wrap up with a few take-home messages. Uh, Although I showed three different simulations, I believe we can use them collectively to comment on the interior fluid dynamics of Jupiter and Saturn. First point is that when you look at the deep outer hydrodynamic layers on Jupiter and Saturn, our simulation shows that it is quite straightforward to generate cyclones and anticyclones, depending on the local shear direction of the zonal jets. And the zonal jets, they themselves can also be easily produced through just purely rotating convection. Second point I want to make is that in case of Saturn, it's also possible to generate polygonal jets through deep rotating convection. And we also learned that giant storms may be shaping the hexagonal jet, but these storms do not necessarily have to be visible from outside. So that aspect can also be modeled through deep convection. Third point I want to make is that our simulation also showed that when a hydrodynamic and a dynamo layer interact with each other, there is a possibility of generating a lot of giant storm activity. And some of those storms can be as large as the Great Red Spot and provides kind of a very natural explanation for forming those. Now, when you take all these points together, and we see that on Jupiter, Great Red Spot might be produced through this mechanism, as I just described, because its dynamo layer is probably interacting with the hydrodynamic layer to some extent. If we extrapolate the interior models about these planets. On Saturn, however, things are a bit more complicated. Its interior structure is not exactly similar to Jupiter. It has been proposed that somewhere in the deep there is a region where there is no convection. Such a layer is called a stably stratified layer. Now, if that is the case, then Saturn's dynamo layer probably will not interact with the hydrodynamic layer because a stably stratified layer acts as a barrier. In such a case, there is no way for convective plumes from the dynamo layer to go into the hydrodynamic layer and excite large anticyclones like a Great Red Spot. So for Saturn, we don't expect Jupiter like Great Red Spot, uh, like giant storms, and which is indeed the case. Large storms are much more frequent and present on Jupiter as compared to Saturn. So it kind of agrees with the overall observation picture. Of course, since life is hard, although these results look promising, a lot more work remains to be done here to better understand the full extent of the convective fluid dynamics of these gas planets. One of the things we really want to capture is that the the westward drift of the Jupiter's Great Red Spot and the the stability of Jupiter Great Red Spot has been pretty much amazing. As I told in the beginning, it has been stable for 300 years, 365 years. And that we could not capture with our model. And we would like to know why and what might help us attain more stability for this kind of features in our simulations. So, of course, I'll just follow that there's certainly something to look forward in that there's a lot of work to be done and potentially exciting new models to be found. And also, fortunately, NASA's Juno spacecraft is capable of inferring the depth of some of the storms on Jupiter in the coming few years. So it will tell us if some of the storms go deep into the planet or not. We know the jet streams go deep, but it remains to be observationally tested if some of the storms go deep or not. From our point of view, at least some of them should. So, and while Juno is gathering all that exciting data, we are also building models that go beyond what I showed you here. Some of the similarities, as I was repeatedly mentioning, were qualitative in nature, and we are trying out different models and see what kind of models can approach a quantitative similarity with the observations. Furthermore, I showed I showed three models and tried to create a holistic view of the fluid dynamics. We are now trying to see if we can produce these interesting results in a single in one model essentially. That will be even better than having three separate models for different things. I have to we have actually made some good progress on this front, and some exciting results are coming. So stay tuned, and hope we should be able to share it in the near future. And on that optimistic and exciting note, I end this presentation. Thank you very much for listening.